So I'm going to tell you about Hess's Law. It's a little different than maybe what most approaches you'll see are, to try to help you understand what it means. So Hess's Law is really just that heats of reaction are additive, okay? And imagine that you're at A, the point A, and let's say this is 50 energy units. It doesn't matter what it is. If you want, you can just put kJ there if you want. So that means A is here. Oops, A is here. Okay, or put it right here next to the line here. Now let's say you go from A to B and it's 25 kilojoules, right? So then A to B is like this, so B is up here. And then B to C is minus 75. So to go from B to C, I have to go 75. So I'll start here and I'll go 25, 50. Well, the lines aren't spaced right. 75 like this. So this is where C is at down here. So this is minus 75, and this is plus 25. Now, if you wanted to know, so these are supposed to represent two very simple reactions of A goes to B, and it's endothermic for 25 kilojoules. And it's B goes to C, that process is negative 75, so it's exothermic for 75 kilojoules. What is the energy for A goes to C? Now, if you just look at these reactions and you add them together, right, what you'll find is that 25, right, plus minus 75, that's equal to minus 50. And furthermore, and that's kilojoules, if you look at how the reactants go to B, right? A goes to B, then B goes to C. So overall, when you add these two reactions together, you might think that you get a reaction of A plus B goes to B plus C, but because B is on both sides of the reaction, we can just get rid of it. So what we usually do, instead of adding it all up and make this really long line, is we just cancel it if it's on opposite sides of the arrow. So you can see that here. This is the process. If you're at A and you're going to C, this is the minus 50 that's here on the graph. So additivity simply means when you add two reactions together, right, that the overall reaction is just the sum of the energies of the two other reactions. So additivity just means you can add them and you get the right answer. This is actually a property of enthalpy because enthalpy is a state function. So this really is a function of all state functions, that their properties are additive. So if you have an internal energy for this same process, you would be able to do the same kind of thing. Well, there's a couple of other interesting things to think about on this diagram. So I'll start with a clean diagram. And again, remember, so this is the clean, I still have this one up here, but this is the clean one. And again, this is energy on this axis now, because we're thinking about these in terms of energy, right? A is at 50, again, and A to B is 25. So if I'm going from here to here, so this is A, and this is B, that's plus 25. What is it when you go from B to A, right? Well, really what you're thinking about then is going in the opposite direction, but from the same start-stop points, it's just if you reverse their order. So this will be minus 25. So if you reverse the reaction, right, this will be minus 25. In this case, let's call it kilojoules. If you were to go from C to B, right? If I was going to C goes to B, then my expectation would be that that would be plus 75 kilojoules. And if I added these two reactions together, notice what happens. The B's will cancel, right? And I have C goes to A, and that would be plus 50 kilojoules. So I actually just reversed these two reactions and added them together. And if you remember from our earlier diagram, C was down here at 0. And what we just said is the process of C goes to A, that's going from here to here, that's plus 50 kilojoules. Okay. So properties of additivity, right? But you can also reverse the reactions. Now, enthalpy is also, again, an extensive property, so it depends on how much material you have, right? So just a couple of quick things here using actual chemical reactions. If you're taking H2O liquid and you're going to H2O gas, that's endothermic, that is, you're vaporizing it, right, by 44 kilojoules per mole of reactant or product. Here, if you reverse the reaction, this is negative 44 kilojoules, right? It's the opposite process. So that actually means when water vapor condenses into liquid, it's an exothermic process. So when you put your hand or your arm over a pot of water that's boiling, you feel all that heat that's being uh, absorbed by your arm. That's actually the heat energy from the condensation of the water onto your arm. And as it condenses, it releases 44 kilojoules per mole into your arm. Now, if I have H2O solid and I go to H2O liquid, right, that's 6.02 kilojoules. On the other hand, if I wanted to go from H2O solid to H2O gas, how would I do it using these three equations that are given up here? Well, I could go like this. It's H2O solid goes to H2O liquid, right? And then H2O liquid goes to H2O gas. So I can add the first reaction to the third reaction, and I'll end up with this fourth reaction that's down here, because the liquids will cancel out, and the energy for this process would be 44 kilojoules plus 6.02 kilojoules, which ends up being 50 kilojoules, 50 point kilojoules, like that, just from the additivity that is allowed for by Hess's law, and all state functions for that matter. Okay, so one other thing about properties of equations. Again, the enthalpy is an extensive property, so it depends on the amount of material that you have in the reaction. So notice that I have this first reaction here. It's N2 plus O2 makes 2NO, and enthalpy for that reaction is 180 kilojoules per mole. What happens when I multiply the whole reaction by a half, right? What do you expect to happen? It's similar to the sort of the idea I said with the gasoline. If I gave you 2 gallons, you could go so far. If I gave you 1 gallon, how far would you go? Well, you'd go half as far. And so, in other words, you'd get half the energy of enthalpy of the reaction when I half the reaction. I think I said that right, from the original. So this would be 90.3 kilojoules. Okay, so we're going to use Hess's law and its additivity and multiplicative properties to take two chemical reactions to find the energy of a third chemical reaction. And let me just say kind of why we do this, because a lot of times people are like, well, why would you even do something like that, right? It turns out like this particular reaction, let's say, to make H2O2 is particularly hard to do. It's actually easy to go from H2O2 to water and oxygen gas, but this particular reaction is fairly difficult. So if you wanted to know how much energy it would take, because let's say you're designing a process for it, what you can do, because of Hess's law, is you can get any two reactions that can be combined to give you this third reaction to estimate what this energy is. Okay, so it's more like an engineering kind of problem. It is also a chemistry problem, but it's kind of like an engineering kind of thing where I want to know how much energy this undone process takes, something that's never been done before. And I want to be able to apply thermodynamics to the problem so that I could calculate, let's say, how much energy consumption I'll use or how much cooling I have to apply to the reaction, things like that. Okay, so let's look at this reaction. And the way I think about these problems, I think of them like jigsaw puzzles, right? So if you're doing a jigsaw puzzle, you sort of have to visualize a jigsaw puzzle. So let's say it looks like this, right? What do you start with? Well, first of all, it doesn't come out of the box like this usually, right? It comes out as a lot of pieces. What do you usually look for, right? you're usually, hopefully you're thinking about this, you're usually looking for the edge pieces. Those are the pieces that are unique because they're all flat on one side, right? And so that makes them relatively easy to place. Like if you do a sky, for example, a jigsaw puzzle of a sky, and all the pieces are blue with white flecks on them, it's just impossible to do the middles. But the edges, because they're flat on one side, are relatively easy to do or find, and then you have to stick them all together. So, what we're looking for is edge pieces, things that occur only in one side of the chemical reaction. So you'll notice H2O2 is over here, and I have an H2O2 over here. So this reaction, right, tells me the picture of the jigsaw puzzle, and these are like the pieces up here. So what it means I have to do is I have to flip this reaction around in order to make it match this reaction. So I'm going to say, well, that top reaction is going to have to be 1/2 O2, and I'm going to leave the states out on this one because it's actually not important for this one, but sometimes you do have to leave the states in, plus H2O liquid makes H2O2 liquid. Oh, and I guess I can leave that out because I just said I was going to leave them out. And that energy for that process is what? Well, since I flipped it around, that process would be plus 98 kilojoules. Okay. Now, notice this reaction. I have hydrogen on this side, and hydrogen, it only shows up in one place, right? It only shows up on the left side over here. So what I can do is I can use this as a guide to say I need to have this reaction. So what I'm going to do is I'm going to write it as H2 plus 1/2 O2 makes H2O, and delta H for that is equal to, well, half of the original value because I halved it. I didn't reverse it, so I don't have to change the sign. But I'm going to go 571.6 kilojoules, and this is what I like to do so I don't lose track of what I'm doing. I just put a divide by 2 like that. Okay. So what happens when I add these two together? When I take the red reactions and add them together, let me change my pen color really quick. Then what happens is that 1/2 O2, now think about it like this, put a line here, we're just looking at the red reactions, right? The 1/2 O2 adds with this 1/2 O2. So I get an O2 in this reaction. And then the H2 comes down from here. So I have an H2. Now, my problem is I have an H2O over here, right? But you notice what happens. I actually have H2O on the left side and H2O on the right side. So these will cancel out with each other. And the only thing that's left then is the H2O2, which then I can write at the bottom here. The reaction arrow doesn't move, it stays in the middle, and I have H2O2. So now that I know that that works, right, that I figured out sort of the way to arrange the energies, then what Hess says is heats of reactions are additive, so delta H is going to be plus 98 kilojoules plus 571.6 kilojoules divided by 2, and that gives us 383.8. And so this is the energy for this process here. And again, what I had to do was use my jigsaw edge pieces, right? The pieces that only show up on one side of the reaction. In this case, it was the H2O2 and the H2 that helped me piece this all together. And then I had to figure out, like, do I have to divide it by 2? And then what do I do with the energies after that? If you flip it around, you change the signs. If you divide it, right, you divide the energy by the same amount that you divided the reaction by. And same thing goes true with multiplication. If you multiply a reaction, then you end up having to multiply the energy by the same amount that you multiplied the reaction by. Okay, so here's another reaction, Hess's Law. And what we're going to do is we're going to use these three reactions, okay, to determine what the energy for this reaction is, okay? And I wanted to point out a couple of things about this, right? And I'll do it on the next page. But this is the formation of NO from its elements, right? And this is the formation of NH3 from its elements. And this is the formation of H2O from its elements again. These kinds of reactions, we'll see, are ones that we often refer to as reactions for something we call the standard enthalpy of formation, but usually that's per mole of product. And so the standard enthalpy of formation, that is the formation of a product from its elements, would be 180.6 kilojoules, then divided by 2 to get 1 mole of NO. But 90.3 would be the standard enthalpy of formation for NO. And I'll go over that definition again. But let's go ahead and solve this problem and see how we're going to do it. Now, there's not enough room here, so what I did is I compressed it all and I stuck it up here. And what we want to do is determine how we're going to put these together. So, and then we'll do sort of the math symbolically down over here, okay? So how am I going to do this? Well, what are my edge pieces, right? Let's start with the first reaction. Do I have any pieces here that occur only on one side of the reaction? Right? What do you have? Well, there's NO, right? N2 and O2, but see, notice there's O2 here and there's O2 here. The N2 only occurs in one reaction, so it's kind of a giveaway that what I'm going to have to do with this reaction is double it, right? So this is what I'm going to do. This is how I actually work these problems out. I'm going to start with the idea of doubling this one. Now I'm going to look for another edge piece. Right, so what does that mean? Well, look, there's NH3 over here, right? And there's no N2 or H3, so that's not a very good guide for all this, right? So notice that this NH3 is over on the left side here, and there's twice as much, right? So I'm going to reverse it, which means I'm going to take the negative of that value, and then I'm going to multiply it by 2, okay? And then what else do I have? Well, I have H2O. Do I have H2O anywhere else? And it looks like I don't, right? There's none in these reactions. It's only in this top reaction on the right side. So what I'm going to do is I'm going to go like this. It's going to be 3 times. Okay, so what I'm going to do now is, this is my guide for both my calculations and for writing the reactions in the next part. I'm going to leave all the phases out because everything's in the gas phase. And I'm going to start by putting my NO, doubling it. So I'm going to go 2N2 plus 2O2 makes 4NO, like that. And the second reaction, I'm going to multiply by minus 2. So I've gone through the thought process of why that is. But I'm going to flip this around. I'm going to double it. So I'm going to leave the arrow in the middle, okay? Don't start them all to the left or to the right, but try to keep it neat and the arrows are all together in the middle. So I'm going to have 4 NH3s on this side. That means I'll have 2 N2s and 6 H2s like that. And that would, energy for that would correspond to minus 91.8 times minus 2, okay? Now, I have my H2s, right, and my H2Os over here. It looks like all I need to do is triple it, right? So if I take 3 times this one, I'll have 6 H2Os. Again, arrow in the middle, like that. And then I have 3 O2s. And I have 6 H2s. Okay, so it's almost ready. I just need to add it together and see what I get. And this is one of the keys about Hess's Law. You really do have to try to add it together and see if it adds up to be the right thing. So I have 6 H2s on this side, right? And I have 6 H2s, so I can cancel it. Anything else that I can cancel? Now, if you said O2s, right, you'd be wrong because they're both on the left side. So they're not going to cancel. What are they going to do? They're going to add, right? But what else can cancel? The N2s can cancel because they're on opposite sides of the arrow like this. So what that leaves me with is 4NH3 plus 5 O2s makes 4 NOs plus 6 H2Os. And we'll double check to see if the reaction matches. And I was careful when I wrote it. I wrote them in the right order. But if you didn't write them in the right order, it doesn't matter. You know, if you had the 5 O2s here and the 4 NH3s here, it wouldn't matter. So that's good. And then the products match. And so that's good. So now I need to calculate my energy. And my delta H for this reaction, and this is how I do it. I would say it's 180.6 times 2 plus, right, negative 91.8 times a minus 2 plus minus 483.7, and then I ran out of space, of course, times 3, and those are all in units of kilojoules like that. And so then you add all this together, and what you end up getting is negative 906.3 kilojoules for the overall process. And that's your enthalpy for that overall reaction that's shown up the top here. And if you're writing the thermochemical equation, which I'm actually not doing, I guess I could, you would just write it like this. Delta H is equal to negative 906.3 kilojoules. And oftentimes, if you don't see this delta H, it means the same thing. The only energy you typically see on the right-hand side is the enthalpy for the reaction. All right. So I wanted to give you just a real quick molecular view of an exothermic reaction. And then we'll be sort of done with this section, okay? So, and this is sort of a tag-on thing. This is the reaction between formaldehyde and oxygen to form CO2 and water. And it produces minus 561 kilojoules per mole. Now, this reaction turns out to be exothermic. So the way that we think about it is that the energy of the reactants is higher. So this is my formaldehyde plus my oxygen. And then over time, what happens is it's transformed into the products, which is my C double bond O, my carbon dioxide, and my H2O, like this. This difference in energy is negative 561 kilojoules for this reaction per mole of formaldehyde, okay? Now, what's going on, right? Why would these be lower in energy than these? And the answer is this: stability. These products are more stable because their bonds are actually overall stronger than the bonds that are shown over here. Now, why they're stronger, we'll have to talk about it another time, but that's coming up in a few chapters. But why they're stronger is simply because they're more stable, they're lower in energy, and there's a stronger force of attraction between the double bonded carbon and the oxygen, for example. And there's some other things going on with carbon dioxide that make this so much more stable. So we have weaker bonds up here, right, that get broken, and the atoms rearrange to form the products. And when they form, they actually form stronger bonds, and that makes them lower in energy. Right? The extra energy, because these are now more stable, is released as heat energy, and that's that negative 561 kilojoules of energy that's actually released in order to form these products.